Thanks so much. It's really an honor to be here. And after the whole day of really awesome talks from experts such as Simon and Bill, I realized that I'm actually basically the boundary between you and the dinner at Palo Alto. So I'll hopefully live up to it. And thanks so much for being with me. And I'm going to be talking about what we do for infrastructure, building infrastructure for machine learning at Facebook. And as a result, I'll first show you one thing that's not infrastructure. And back in the days when we were doing machine learning, then and especially deep learning, then we started at Berkeley and we're building really crappy machines that have GPUs in it. Actually, GPUs are more expensive than the machines back then, and everything worked very nicely. We're able to train ImageNet. We're able to write software that runs pretty well. And at some point, we're like, it works. Now we want to scale it. And ideally, then it becomes the question of how do we scale it to an infrastructure level or like a data center level so that we can serve 2 billion users at Facebook or basically allow people to train very large models that ships to self-driving cars and stuff like that. The reason we care about it is because since 2013, I think we've seen a booming number of interest in machine learning, especially deep learning. And the really classical paper, which is using CNNs for classifying digits or documents, that actually has seen like a surge of the citation numbers since 2013. And for those folks who actually lived through the days of that plateau and doing grad school life and stuff like that, I feel you. And that was the time when we felt a little bit depression of what ML should do. But today, I think we're all very proud that everything is working very well, and we're actually able to do something that matters for humanity. And from a researcher's perspective, when we think about machine learning, what we do is basically saying we have a bunch of data, such as ImageNet, living on disk, and we extract some features out of it, or sometimes we just take the raw data, such as images or audio, and we have some models, we train it, and we look at the performance. If it is good, we proceed with inference. If it is not good, then we basically retrain the model, tune some parameters and stuff like that. The training happens offline, and then when we get a model out, we basically put it online and ship it to the final server side. And when we talk about things under the scope of actually having a product, then often there's a little bit more stuff involved, which is when we are doing inference, how do we properly define models and ship it into a cluster of machines? How do we make predictions connected with the product side? And more importantly, because machine learning is basically very largely dependent on data, how do we make sure that we have a proper data pipeline that collects, such as user feedback and things like that, put it back into our database so that when we're training things in the next time, then we're able to use these larger amount of data to train better models and stuff like that. And that essentially basically gives us a pretty good challenge across multiple axes of this toolchain. So usually when we are training with ImageNet, it's pretty fine. We just have an SSD, and then everything is just loadable from local disk. But if you want to train even larger amount of data, such as the Facebook user profiles and stuff like that, then there's a big storage challenge because you cannot definitely put it on a phone or on a laptop, and it's usually involve terabytes or sometimes petabytes of data. And then when we want to train stuff, then we need to transfer things from that big chunk of data storage to the machines that are actually doing the computation. So that involves quite a bunch of network loading and communication overheads. And during offline training, we know that machine learning actually involves quite a lot of computation. So it involves quite a bunch of computation challenges as well. When we are doing the training to inference conversion, sometimes a lot of things need to be happening in an online training fashion, meaning that as the user data comes in, we actually want to update the models real time. So that also involves quite a lot of communications. And of course, inference today is actually not that cheap either. We actually need to do pretty powerful CPUs or GPUs for inference, especially for computer vision and other use cases. Now, over the years, we often receive questions like this. People ask, does Facebook use machine learning? And do you guys do hardware? What do you guys do for hardware of machine learning? And what kind of software do you use? What kind of tool chains do you have in Facebook? And what kind of things you need to do to deal with the scale of Facebook? And we figured it was probably pretty nice for us to basically share more knowledge and share more experience that we got over the years, and also, more importantly, share the principle that we use to design the Facebook AI infrastructure to allow us to do machine learning at a big scale. So do we leverage machine learning? We definitely do. And it actually spans across a large number of different use cases that calls for different machine learning algorithms. Newsfeed, for example, is basically our primary interface to the users and ranking the news in the news feed and similarly ranking things for ads and allow users to search different contents and stuff like that is one pretty prominent use case. And when we are doing, like say classifications of faces or classification of different objects and stuff like that, we have Facer and Lumos, which is our computer vision engine. And we also use machine learning to do a lot of language translations and speech recognitions because we actually span quite a lot of countries. So we are actually like dealing with tens or probably hundreds of languages that we need to translate between them without problems. And with these kind of use patterns, then what we see is that we adopt a wide range of machine learning algorithms. And you might be a little bit surprised that it doesn't always goes to deep learning. So there are some really simple approaches, such as like SVMs, that works really well. So imagine you want to classify a face. That is basically whether it's it's me or someone else. Then after extracting features from CNN, it's actually very quick and effective for us to train a tiny SVM model that does the predictions. And for things such as like Sigma, which is I think our search engine, then we found that classical things such as GBDT actually works pretty well. We tried to get rid of GBDT and then use an MLP for that, but we found that like combining this with MLP approaches actually works often pretty good. Multi-layer perception is actually one thing that runs for a lot of the services, and we're going to be touching this a little bit later as well. The pattern is that like unlike CNNs, which involves a lot of computation compared to the memory access, MLPs often involves quite a large amount of sparse data. And we basically like take that sparse data and then look at the corresponding rows in a huge lookup table. And as Jeff mentioned earlier today as well, then those kind of lookup tables are like pretty huge, probably hundreds of megabytes or gigabytes of size. And then we basically randomly access the different rows and do simple summations or weighted sums out of that. And that involves quite some different challenges computation-wise compared to the CNN and RNN applications. And of course, we use heavily the deep learning approaches such as CNNs and RNNs for vision and other perception use cases. When we look at how often we train those kind of models, then they pretty much boil down to how fast the data changes and then how fast we would like to run those models and how fast the models evolve. And for things like newsfeed and ads, then because everything's like changing so fast at Facebook, we actually need to train them in a very frequent fashion, probably in a sub-day kind of fashion. And then for models such as computer vision and like faces and stuff like that, because dogs don't really evolve that fast, we can actually train things every couple months or things, and especially when we have new models, and then the frequency gets a bit lower. These kind of models also train with different, time span. For computer vision models, often they they're trained with about hours or sometimes days for face models with really large data. And for models such as newsfeed and stuff, then we train it in a sub-hour kind of fashion. And especially when we're doing online training, then we actually do the model flush every couple minutes or seconds or something like that. What's really interesting is when we look at the overall workload of machine learning that we are having at Facebook. And often people feel that we are having a lot of CNN use cases, because when we talk about self-driving cars, which is actually a pretty valid use case of deep learning, then there's a lot of visibility of computer vision. But when we think about the use cases and we look at the use cases at Facebook, one thing that we found is that there's a lot of ranking use cases. And if we're going to be comparing the relative importance of different models, then what we see is that speech and language are probably spending quite a little bit of time on the very right side. And then computer vision use cases, because they are actually very expensive CNNs, are a little bit more expensive than the language and speech models. But the real workload is often basically the newsfeed ranking and ads ranking cases, because every time a user goes onto Facebook, then he hits the newsfeed, and we need to very quickly rank those kind of things. And that's probably one of the most prominent use case of machine learning over there. And that becomes a little bit interesting, because when we talk about the neural nets that runs the ranking models, then they are actually more memory-bound than the CNN compute-bound applications. And that actually also triggers us to think more about what kind of hardware designs that we would like to have for coping with different computation patterns. Now, going to the next question, does Facebook design hardware? And the answer is yes, we do. And we adopt a very a simple strategy, which is basically saying instead of finding one single machine type that serves all the needs, we actually identified a wide range of use cases inside Facebook that has different characterizations of memory, of computation, of disk, and stuff like that. And what we do is we basically find a small set of customized and dedicated hardware to serve different needs. And let me just go through a bunch of them that are pretty interesting. For the web tiers, basically like the service that we do for serving WWF and things like that, what we found is that it's basically just doing a lot of I/O. It's loading the data from the data storage and serving it and stuff like that. So we really focused on power efficiency and also kind of like the size of these kind of machines. What we do is we have a sit-in in an Open Compute Summit, Open Compute project called Yosemite, which is basically these units that holds 4 machines, what we call twin lakes, in a 2U rack that's like 3 on 3 sides. And what happens is basically for a 2U unit, we have 3 of Yosemite components over there with 4 machines in each, with a total of 12 machines. And those kind of machines are pretty power efficient and with single socket CPUs serve the throughput very well. And we go to the compute heavy units on the CPU front, then we basically design 2 socket machines that have a pretty nice like CPU and pretty good amount of memories, and then we'll put them side by side so that instead of 12 Yosemite machines, twin lake machines, we have 3 Tioga Pass machines that allows us to have a very powerful CPU machine that can cope with large amount of memory as well. And for the storage, then we basically design what we call Bryce Cannon, which is essentially just like storing quite a lot of disks with a head node that's Yosemite. And what it does is basically we had a pretty nice name for it called JBOD, and it's basically just a bunch of disks. And it allows us to have very high throughput data storage and data service. And so, of course, everyone talks about GPUs, right? In 2013, we started basically kind of similar to the very first picture that I showed. We started with off-the-shelf GPU machines. We used HP service, and then we learned quite a lot about the serviceability, the thermal, and the perf reliability and cluster management situations. And then later we designed, also in the Open Compute project, and what we call Big Sur, which is basically a 3U machine that hosts 8 NVIDIA M40 GPUs. This year we updated this to Big Basin and also Big Basin Volta, with the slight change that we basically put the box, the big one, as a pure GPU box, and then we isolated out the head node, which is basically the CPU machine, and we put a Tioga Pass over there, and that allows us to basically, continue providing a pretty reliable GPU service for all our use cases. What happens is basically in this pipeline, we have data, which is served by Bryce Cannon and the different data machines. And then for the training and evaluation, we use the pretty powerful Big Basin or Tioga Pass to basically train the machine learning models. And when we want to ship it to inference, then we use Twin Lakes or Tioga Pass, depending on how heavy computation-wise they are, to serve these models. So that's basically how we put the hardware together with machine learning. And next question is, of course, what kind of platforms do we use? Right? And similar to the different wide characteristics of the hardware needs, then we also see that we apply the same philosophy to the software side. We see the wide range of need for machine learning software, and we basically design different pieces of software that allows us to adapt to different use cases pretty well. So for the frameworks that we talk about in Facebook, then we usually use 2 major frameworks. One is Caffe2 for production, and one is PyTorch for research. And the principle we use is basically to look at the efficiency that we want for frameworks. One is infrastructure efficiency, meaning that we want to run things fast, want things to be highly scalable, and want to be able to plug into different hardware backends as easy as possible. And one is basically developer efficiency, meaning that we want to expose as much knobs as possible to the users so that researchers can basically break stuff, make things run fast, make better models and stuff like that. On the Cafe2 side, what we focused on is basically to plug it to different backends, such as NMPAC on the GPU side, OpenGL for the mobile side, and CUDA, of course, on the server GPU side, to allow us to run things efficiently and across multiple platforms. And that allows us to basically train a machine really fast or deploy things onto the mobile front and stuff like that. It also provides us a harness to plug in new directions to further the performance. And one pretty important project that we recently released is called tensor comprehension. And what it does is essentially, like when we think about Anima's earlier talk, we talk about the fact that there is quite a lot of tensor computations that's needed. And essentially, tensor comprehension allows you to write in very simple Einstein notations, similar to the ones on the top. And then it uses compiler technology, in this case, the polyhedral optimization, to figure out when you carry out this mathematical computation, and whether, like how you should break down the little blocks that are aligned with the cache, and then how do you schedule the computation dependent on the hardware characteristics. And it does all those optimizations for you so that you don't really have to write C code or CUDA code, which is often really hard to optimize for. Now, that's basically infrastructure efficiency, meaning that we want to run things fast. But on the other side, researchers were sometimes like, we don't really want to run things 100% efficient. We are okay with 20% efficient. And all these kind of infrastructurally efficient frameworks, such as the all-day Caffe or Caffe2, and with all due respect, TensorFlow, has to challenge that it's a DSL. And every time we talk about DSLs, the problem is basically like, it's a little bit hard to debug, right? And so people basically shout that we want to use Python. It's probably the perfect time in the afternoon for you to read some code. And so for PyTorch, what we did is basically we made Python basically a first-class citizen. And we made the code and the programming model much like NumPy or Python. And please don't really read that code. And basically, if you look coarsely, then the PyTorch code looks much like NumPy. Like, it doesn't get into your way when you are thinking about how you run models or how you design models and how you run models. If something goes wrong, it breaks at that exact point and it gives you a Python stack trace, and you can do PDB and stuff like that to figure out what went wrong. You don't have to go back into a protobuf to figure out what went wrong, and it made all those kind of researchers' life really well. And we got user testimonials. Thanks, Andre. And there are also people talking about the fact that you should talk to a doctor to find out if it is fit for you. We love that one, and thanks for the warm comments. And then we often got this question. People are like, Yangqing, you must be bullshitting, because you have two frameworks, and it must be very difficult for you to actually transfer things around, right? And we were like, acknowledge this is actually one problem. And the more prominent problem for the industry is that when we're having a hell lot of different frameworks, and they all talk about the same thing almost, which is CNNs, RNNs, and MLPs, but they use a slightly different dialect. And to make matters worse, when we talk about our really awesome hardware vendors and hardware partners, then there was like, what framework do I support? Because there's, as quoting one really nice gentleman from the hardware side, he's like, I have 14 frameworks to support, which is not really great. And if we have to do things one by one, then it doesn't really get very well. So earlier last year, then we designed, or we proposed this open format called ONNX, Open Neural Net Exchange, that tries to help the community to unify some of these kind of challenges. What we observe is that a lot of the flexibility that researchers use, such as training and experimentations, actually do not block the shipment. Because when we talk about GANs, for example, then there's really crazy logic to basically connect the generator with the discriminator and like the data pipelines, things like that. But when we boil down to the shipment side, what we have is a CNN model. And as long as we have a proper definition of these models, and we plug in the different frameworks on the top and the different hardware implementations at the bottom, then that allows us to very cleanly define a contract between different places, different frameworks and tools, so that we can unify the tool chain much better. And we realized that, like often when we talk about standards, then there are already 14 standards, and we might be creating the 15th one. So we really took a lot of attention into it, and we're basically consciously making Caffe2 and PyTorch interface with the ONNX models, and we're actually also partnering with NVIDIA and a lot of really nice hardware vendors and partners to push ONNX so that it can can really serve the community well with a neutral party. And so that's basically what we have right now. We have the top, which is basically the computation patterns of machine learning. At the very bottom, we have the hardware that serves different purposes. And then in the middle, basically, we have the Caffe2, PyTorch, and ONNX, and also the APIs that we built on the data front and the service, prediction service that we built on the inference side that basically puts the machine learning models. Now, another tricky question that we often encounter is basically saying people try out Caffe2, try out PyTorch, try out TensorFlow, and so this is great on a single machine. But if I have a cluster, how do I properly manage the resources? And at Facebook, we basically built another layer, which we call FBLearner, that helps us to manage the workflows, manage the different models that we run, manage the machines that we allocate, and then also helps us to package models for deployment. What it does is it has three major components. One is feature store that allows us to store different type of data, and also exposes a feature I/O interface so that when we run some machine learning training, then they can basically directly get a clean API from the FBLearner site. And FBLearner flow then also then takes care of requesting a bunch of machines and setting them up in a kind of like mini cluster environment, hosts the computation, training, or data preparation, and finally packing the model. And then on the serving side, then we have FBLearner predictor that allows us to basically have a clean interface for the very vast number of clients when they want to serve machine learning models. They don't really have to write their custom inference model or inference code or plumbing code. They can have a very clean interface to plug into their products. And essentially, when we talk about the workflow, then FBLearner feature store takes care of the data and feature part. It often runs on the CPUs because it's very throughput-oriented. FBLearner flow then takes care of the training part and a little bit of the evaluation part as well. It uses CPUs and GPUs. And on the serving side, then predictor takes care of that, mostly on CPUs today. And that's because we have a vast amount of CPU machines that are pretty efficient in deployment. So putting all the things together, then what happens is basically on the very bottom, we have the hardware side. Then we have a layer of FBLearner that allows us to interface with hardware and software, especially the machine learning software. And then we have a layer of machine learning software that interfaces with the users so that they could write models, train models, and deploy models. And that supports the very top machine learning use cases that we have. And we use this to serve about 2 billion people. And of course, that involves quite a lot of challenges and also opportunities, actually. Talking about the details of it is probably a story for another day, especially since we are a little bit approaching the limit. But I kind of wanted to point out that we have lots of data that's scattering around all our data centers, and we have lots of compute. And one particular opportunity that we see is that for the different regions in the world, then people have different use patterns, right? So the US is probably using Facebook most of it during the daytime, and of course, if you are going to to Indonesia, then due to time zone differences and stuff like that, then their use pattern is slightly different. And because we have a huge amount of data centers across the world, and also kind of serving different purposes, then we have it's a pretty big challenge for us to balance out the load and also utilize the unused resources when the usage from the user side is low, so that we can basically pace out the whole. We can pace out the load and then also to use the resources most efficiently. And one pretty interesting story is when you go to 101s and when you drive on 101 and 87, sometimes you find that there's constructions going on, and it's usually pretty disruptive, right? And at Facebook, then we don't really want things to be that disruptive. And one thing that we often do to make sure that we are actually serving the different ML use cases and Facebook use cases well in general is that we often randomly shut off our whole data center. Someone comes in and say, where's my data center? And we use that to basically test if our infrastructure, both machine learning and also the general service, is actually stable enough for us to serve all the use cases without having to be disrupted when we have even one data center down. And that actually makes, helps a lot for us to build a large-scale infrastructure that serves the various use cases. And just to summarize, then, so basically we do use AI in a lot of places. We use that to infer information from lots of data with a wide range of models, some deep learning, some classical. And there's a bunch of challenges when we are talking about machine learning at a global scale, but it's a pretty nice work. And if you open Facebook and it's working, then it basically means that infrastructure is doing a really great work, right? We have the joke that infrastructure is only visible when things are broken. And because no one feels that Facebook is broken all the time, it probably means that this set of really awesome colleagues are actually doing a great work. And I want to basically give a shout out to all of them. And we together built this tool chain. And I think if you want to learn more about it and if you'd like to join us, then pin any one of us, and we'll be definitely more than happy to chat in more detail about that. With this, I hope I'm blocking you guys for dinner, and I can probably take a few questions.
Thanks, Yangqing. We can take questions.
Thank you for a great talk. I just had a question for you. You talked a lot about learning in the cloud, right? But
right.
You have this army of devices out there that are getting better and smarter.
Right.
Do you, right now or in the future, foresee learning to be distributed, like some federated learning type?
Yeah.
Or maybe you do it now, or maybe just like some feature sort of design or like data imputation.
So yeah, so basically the question is, how do we deal with the vast amount of mobile devices out there, right? So I think we are probably the first company to actually ship machine learning models across all the major mobile devices today. Right now, I think what we do is it's more about inference on the devices right now, and a lot of the information, because a lot of the information actually hits the Facebook server anyway, we find that often training on the server side still kind of makes more sense. And of course, as we look into a lot of the privacy-aware data, then it makes more sense to train things on the mobile side. And I think right now our philosophy is we don't want to disrupt users' privacy. And then right now we don't really have training models training on the mobile side, but it's definitely a pretty interesting direction to look into. Thanks.
Hi. So you mentioned Facebook has about 2 billion users, so I'm assuming for each user you have lots of data.
Right.
So do you guys go through any kind of pre-processing before you start feeding data into the models?
So this is probably a little bit more on the product side, and to be completely honest, I'm not quite familiar with that. I think one thing that's that we got told all the time, and is actually pretty strictly enforced, is that if you're going to be accessing users' data, it's pretty strictly forbidden, and it's one of the reasons. It's one of the few solid reasons that you can be fired within 24 hours. So yeah, we take pretty good care of that. So, and to your question, I'm not quite sure about how we deal with that in detail.
Thank you.
Thanks.
Thanks, Yangqing, for the infrastructure overview. So you talked more about the training side of the platform, but
right.
Facebook is one of the largest edge device inference, product.
Right.
So how do you deal? We heard a number of model compression and for inference techniques. Is there some general pointers that Facebook does, low precision inference or something on the edge?
Yeah, so we actually already shipped something on the edge, and one example that I can show is, for example, last year when we were releasing the style transfer models, then what we also shipped was kind of some level of compression, especially on the sparsification and model compression front. We haven't got the computation to be completely sparse yet, mainly because, as Bill mentioned, and it's easier to do sparse computation on the specialized hardware and not that easy on existing hardware. And we do have early results and experiments using low precision computations. Last year in NIPS, we had a paper talking about software implementations on ARM platforms to do 2-bit and 4-bit computations, even under the 8-bit, int8 kind of computations. So I think that's a very interesting direction. On the edge, then, as Bill mentioned, it's lower bits always saves a lot of power, which is something that mobile is pretty critical about. So yeah, I think we do have quite a bunch of work on this direction. We have shipped some of these services, and I'm really looking forward to have more like research and applications popping up on that front.
Yeah, in one of your earlier slides, it looked like you were exposing the LLVM internal representation in your workflow. I was wondering what benefits you got out of that.
So basically, you probably mean the tensor comprehension one, right? So basically, essentially what we do is we want to have multiple levels of IR that can help us to model the computation from the more mathematical side to the more compiler side. Tensor comprehension, there's actually a paper out, so you can read more details about it. We kind of focus more on the very top, like Einstein expression front, and also the halide IR part, and then lowering it to polyhedral IR. This part is basically kind of like code gen from either LLVM or using MERTC, which is NVIDIA's code generator. And so for LLVM IR to the actual binary code, we literally just utilize LLVM for that.
Okay, thank you.
Thanks.
Let's thank Yangqing one more time.
Thanks so much.